So in this video, we will introduce actor-critic algorithms. So in the last video, we talked about policy gradients, and we came to the conclusion that variance is a real big issue when we train policy gradient algorithms. And the thing with variance is in the estimation of the policy gradients as we did it so far. So this is actually the last formula that we have, where we take Monte Carlo samples in order to calculate over the reward to go, and by subtracting some baseline, an estimate of the policy gradient that we average out, that we can then use actually to do an update step of our policy. And the general thing with variance in this target is we already actually reduced our variance as we introduced the subtraction of a baseline function. However, we estimate this actually the estimate of the reward to go, which is actually an estimate of the Q value of ST80 at this point, is actually estimated through a single sample that he sampled from the environment, and this sample is, as usual, prone to high variance. So the general idea in actor-critic reinforcement learning is that we use, then instead of using a sample-based estimate of the Q value, we actually use a critic that helps us to estimate the Q function. So in this setting, what we actually will be doing is we will introduce a framework that is called actor-critic, where we have two different neural networks or functions that we will simultaneously optimize. One is the actor, which is basically our policy that gives us actions in certain states, and critics that actually approximate our Q function and that actually tells us how good the value is that we are currently in. So actually we already talked about the actor very much, because this is actually the policy. We did that actually through policy optimization in the last lecture. Still left open is actually how to come up with a critic that actually serves as what we wanted to serve in this lecture. So in practice, we already know Q pi is something that cannot really be computed, or cannot be really something that we can hold in memory through a tabular representation or something like this, which means that in practice we need to approximate it with a neural network that we define over some parameters phi, and we want to train it with standard gradient descent over k epochs, minimizing some error metrics such as the mean squared error. So this is usually what we will be doing in this setting. So we want a Q function that we actually learn, and we can actually plug in here. So the general idea is that because of the Monte Carlo policy gradient being sampled and hence having a high variance, what we want is we want to use a critic, which is in this case a neural network as we have used it in DQNs, and we want to use this critic to estimate the Q in here, and meaning that we want to have two sets of parameters that we train separately. One is theta that we actually use for our actor, and we will train it using policy gradient, and the second set of parameters phi, which we will be using to estimate a value function with one-step TD or something like this. And we will use them in order to actually estimate the gradient. Such algorithms are actually called actor-critic algorithms, and they have actually also an early side note is at this point. We also did that when we did Monte Carlo policy evaluation, where we actually introduced time difference learning to trade bias for variance. So we took out the variance, and we instead updated our targets, or actually updated what we have been doing towards a bootstrapped target. And this is actually what we also will be doing in here. So we will actually not use the sample-based estimate of Q, but our neural network or our critic that estimates Q. And we will use this actually as a target for our policy gradient update. So we will introduce a little bit of bias as we now approximate Q with a neural network instead of using the actual sample that we obtained from the environment. One thing left open is I told here that we usually update parameters theta of the state value function in this case, although we need the Q function. This is the thing. So why actually are we doing this? Typically what we will be doing, this is also something that you have seen a lot in TD learning. Typically what we want to do is we want to estimate the value function using a neural network, and we want to estimate it really explicitly and with high accuracy. And then we want to sample the Q value out of the value that we have, out of the state value that we actually approximated using the critic network. How can we actually do this? So actually, if we have a good approximation for our state value function, what we then can do is we can approximate the one-step return easily by taking the immediate reward we get plus some discount value times the value of the successor state that we actually end up in. And this basically means that we now arrive at an approximation of our policy gradient, because we actually now because we are now actually using an approximate gradient, and this approximate gradient points into the direction that is being suggested by the critic network, which is actually in here. So we can easily plug this one in here, and we end up in an approximation of the Q value of the reward to go that we actually have defined in the original version of the policy gradient. Okay, so if you do something like this, so we will actually use this approximation. What we actually will be doing is, this actually is approximated, so we will not have the real target anymore, meaning that we introduce a little bit of bias in the estimation of the gradient. However, if we now put that into here, which is actually then, what we actually want to do in here is, we have seen this in the vanilla policy gradient algorithm in the previous slide. So we want to define the advantage of the policy gradient, so the advantage of the action in a certain state. And we see at this point is that we can, like, embarrassingly easy and straightforward calculate the advantage, for instance, using the time difference error. So in this case, if we just use the advantage at this point using the thing that we just defined is, usually we have the advantage being defined as the advantage of an action in a state ST is nothing else than the state action value of this stated action pair minus the state value itself. And if we now take this down to the one-step TD update that we actually defined in the previous slide, we can reformulate this given as the immediate reward that we see in this state plus the discounted value of the next state minus the value of the current state. So this is actually the advantage. And actually the V function is the thing that we actually approximate using our critic network. And this actually means that we can take the immediate information that we get from the environment and just need a neural network that we use to approximate the state value function. This also defines a more general framework that is called generalized advantage estimation, which is like really similar. So if you get the intuitive understanding behind the n-step returns that we introduced in TD learning, where you actually had, like, on the one side the biased one-step returns of TD learning versus the non-biased but high variance n-step returns of TD learning, and we had like the all the variance in between, where we can actually take like more sampled rewards into account. This is something that we can also use in here, so we can calculate the advantage either by just taking the current value and the next state value into account and taking into account the immediate reward, or we can sum it up by taking the one step and the second step reward into account and estimate and go on and use the value of the upcoming states into account. So we can come up with a generalized advantage estimation that, given a parameter, in this case k, we can like define how much bias we want to trade over variance when we are actually estimating the targets that we use for our policy gradient update in here. Yeah, so Actor Critics just being an approximation or like an introduction of the idea that we actually used in bootstrapping and TD learning into the policy gradient estimation, into the policy gradient update where we estimate our gradient, and where we have the problems with high variance. We also can trade variance over bias in this setting using a generalized advantage estimator at this point, and to use a neural network that we can use as a critic that suggests the direction of the policy gradient. What we also see is, what we also see is that, this is also what I just told you, if we take the full returns into account, we have a high variance target. Actually, if we take one step TD, we have a high bias, but nearly to zero variance, just one reward that you take into account. And we can also take in between steps that we have also seen in end-step TD learning. Still being valuable to know, approximating the policy gradient introduces a bias. And you will see also that it is important to use on-policy targets in this case because you're updating the policy parameters with respect to the sampling of the environment with your current policy, which is something that is always giving additional bias into your optimization if you not account for it explicitly. However, we will also see in methods such as TRPO in the upcoming videos that you can a little bit correct this via important sampling. And also one thing to actually maybe use actually the advantages of both methods, so full returns of one step. And a good idea is also maybe to bootstrap Lambda to actually bootstrap your number of returns you take into account whenever policies differ, and then you can go larger, then you can actually trade bias over variance during the course of training. Okay, yeah, so actually one more thing to add at this point. I talked about on policy targets, and why I said this in this case is actually because the bias that you actually introduce in here, because actually policy gradients by definition only work on policy, meaning that you want to increase the action in the state of the policy where you currently rolled out the trajectory. And if you now actually change the target and you introduce a bias into the policy gradient estimation, this is something like really similar to making it a little bit off policy, which is something that you really need to account for. Yeah, so actually what we did, maybe to sum up this a little bit, also the policy gradient itself, we did not explicitly talk so far about continuous action spaces. However, because we directly update the policy parameters currently, or the parameters of the policy, we can also easily deal with continuous action spaces. In fact, most of the algorithms discussed so far can be used for both discrete and continuous action spaces, while, of course, exploration in high-dimensional continuous spaces might always be a challenging thing to do. While there is actually many ways to do this, I will just introduce maybe the most straightforward idea to actually use continuous spaces. And the most simple idea is basically to use a Gaussian policy. So usually, because this is a very common thing to do, so in continuous action spaces, usually you do a Gaussian policy that is defined by a mean of some function of a state. For simplicity, let's just consider that we have a fixed variance, which we might also parameterize, but it makes things a little bit more complicated. And we just define our policy to be a Gaussian, and our neural network just predicts the mean of that Gaussian distribution. Learning this policy can also really be easily plugged in, because we just in order to actually calculate the policy gradient, we can just calculate the gradient of the log of the policy, which is defined like this. This is well understood for Gaussian policies as well, for Gaussian distributions as well. And you can use this, or you can plug this in if you want, just try it out, using, for instance, in reinforce or also in advantage actor-critic algorithms. So you can really just put this in, and you have a continuous action space that you can sample actions from. Yeah, exactly. Okay, so to conclude policy-based reinforcement learning, so the introduction, we will go into a few of the latest algorithm as well. But all of them actually use the same intuition behind them. So they have a policy and they derive a policy gradient, and the policy gradient is being optimized. And the question is always how to estimate the policy gradient or how the policy gradient looks like. And we have also seen different variants on them. Variants of them, which are actually not that different from each other. So in reinforce, our policy gradient was just being derived by the return of the episode. Then we introduced baseline functions, which actually helped us to reduce variance, where we only only used, for instance, the reward to go, or where we also subtracted a state value from the state. Then we introduced our advantage actor critic idea, where we said, okay, we do not use the sample estimate of the return, but the return, we estimate the return by approximating them over the critic, which actually introduces bias but trades a lot of variance against it. And there's also a little more different algorithm, which is called deterministic policy gradient, which we will introduce in a video on deep deterministic policy gradient, which is another variant of doing policy gradient algorithm, but that's a little bit other than the other ones. However, all in fact lead to a stochastic gradient ascent algorithm that is used actually to update the policy parameters. And in any cases, the critic uses some policy evaluation to update, to estimate Q or V. This is also an image that you see a lot, introduced by Sutton and Bartu initially, where you just say that you have a policy and the policy selects actions in the environment, and through the reward in the environment and the state, you approximate a value function. And in order to actually, in order to update or train the policy, you use the TD arrow from the value function together with the current state and the action in order to update your policy parameters. So this is actually a picture for actor-critic policy gradients. Okay, so conclusion in a sense for policy-based reinforcement learning, what you have seen, maybe it is substantially different from what we have seen with value-based reinforcement learning, in particular with DQNs. So there is no replay buffer in policy gradients, there is no stored experiences that we can reuse, because we actually learn directly on policy, which also means that once we have a batch and we have actually updated our policy, we need to discard the experience, because actually we cannot use the samples to estimate the gradient again, because the gradient now would be different, meaning that in general policy-based reinforcement learning can be adjusted to be less sample efficient. And it is also not very easy to really use experience replay memories as we use them in DQNs, while we can learn off policy a bit through the application of tricks such as importance sampling. It is only usable, we can only do this in a very limited fashion. This is also what you see here. This is just a plot where you train two algorithms, and what you usually see is that the performance of value-based reinforcement learning methods in terms of sampling complexity, of course depending on the problem, is usually higher if they are able to solve it, because they actually can reuse samples of experience. One more thing, talking about exploration and exploitation in general for policy-based reinforcement learning, we will have a lecture on exploration strategies as well, but now really for policy-based RL, policy gradients only consider the improvement under the current data, and this also means that it's easy to get stuck in local optima. So actually we're improving a bit in our policy in a direction, and this also means that we can get stuck. Could we use epsilon greedy? Yes, but it is not really ideal, because we are estimating a gradient with respect to the current policy, and widely different actions cause breakage in the gradient estimation. And also the thing is, the exploration is mostly uninformed about the current best guess. So actually epsilon greedy is just saying with some probability epsilon take another action. And this is not like really mathematical profound for the estimation of policy gradients. An alternative idea that you will see also a lot in practice is that you make sure that the entropy of your policy is not too low, so that you will have, like, you estimate the probability distributions of your action over the states, and you want to maintain some entropy so that you will not always select a certain action. This can be easily done with an additional regularization term that just pushes the entropy up at each step, so that you actually, like, keep on having an explorative nature in your system. Meaning that you encourage a little bit exploration, but do not pick fully randomly in a sense. You may want to increase variance in Gaussian policies, for instance, or make a softmax slightly more uniform. This is actually what you will be doing in fact. This is also something that you do with the KL the Kullback-Leibler divergence regularization in TRPO, which we will see in upcoming videos, and it works really well in practice. So this is actually how you deal with exploitation in policy-based RL if you want to do it. So there's also, like, coming back to our initial statement, the thing is, if you want to solve a problem, better be careful and solve the problem. So if you want to try to solve a problem the direct way, this is a good thing to do, but as you're sampling the environment of a stochastic process, maybe you need to be really careful and handle the high variance that you observe in your system really carefully to actually not end up in a situation that actually helps you to not recover anymore. So there's also some references that we used for these slide decks. You can also dig into them a little bit more, and we will introduce a few policy gradient algorithms in the upcoming lectures.